All right. So today we're going to keep. Actually, let's make sure this is getting the audio. Was anyone able to actually view the video by any chance, by the way? Did anyone take a look at it? The videos that were online? Just to see if they work for more than anything. But it's fine if you don't. You're here, so you don't have to. But to see if they work more than anything else. You get the link, people. I sent the link out. Everyone got that, right? Okay. So today we're going to talk about a couple things. I'm going to finish up the prerequisites for the course. I didn't spend too much time on this slide last time. I started to basically start this slide, but then I didn't really finish it. So I wanted to go over it in some detail just to cover a little bit of the background of what you might, I'll phrase it as what might be helpful for you to know before taking this course. As I said, there are no official prerequisites for this course, largely because people come from a lot of different departments to take the course. So we're not going to have an official, you have to take linear algebra, this course number before doing this course. But if you have no experience with linear algebra, this could be pretty tough. So a basic background in linear algebra, as well as some background in programming, does end up being a pretty relatively important for taking on this course. I think it'll be tough if you don't have either of these. That being said, not today, because I actually ended up deciding that it'd be better off to just kind of jump into a little bit of the material to get people excited rather than doing 2 lectures of background material to start off with. But next week, starting on Tuesday, I'll have a review session for the kind of linear algebra and some MATLAB that you will need for this course. So it's going to be very basic because it will be a review. It's not a replacement for an entire semester's worth of linear algebra by any means. But it will at least hopefully reinforce some of the stuff and maybe highlight some of the things that you maybe kind of forgot from your last linear algebra course that are now important to pick up again for this course. So we'll do that next Tuesday. We're going to have this review of linear algebra and MATLAB. If you are completely confident in both those things and are sure today's lecture is a breeze for you, nothing is confusing, you're welcome to not come to that. It is optional. The videos will also be online, so you can always brush up afterwards if you want. Typically, I do want you to come to class, but for this one, because it's a review, for those that are completely confident in their background, it's optional. But I'll have it during normal class hours. So come if you have any sort of concerns about whether or not you grasp all the material from, not this little bit here, but from the lecture today. So in terms of the actual prerequisites, as I said, there's 2 real things you need to know. You need to know, to do this course, you need to have some background in programming, because we are going to be focusing on implementation here. We're going to be coding these exercises, these algorithms I'm talking about in class. We're not just going to talk about them, we're actually going to code them, and you will actually run them on real data. This is really important. I've always felt like I don't actually ever know that I understand an algorithm until I can actually code it. That's sort of always been my check, whether or not I actually understand it or not. And so we do need some programming for this course. This is also a computer science course, so that probably isn't too much of a surprise to people. The one thing I'll say is that if you have experience in a language other than MATLAB, that is okay, but definitely come to the course next time then. Because MATLAB, it's more or less the same, and certainly at the level we're going to be using it, if you have other programming experience, you'll pick it up very, very quickly. But we will still be using MATLAB. You will still need to do that, so do come to the course, especially if you haven't had a lot of experience with MATLAB so far. So maybe I'll close the door too, just to drown some of the sound. Yeah, it's a question.
So just a quick question on that. I mean, are we going to be turning in MATLAB code and then running it?
The way I will typically, right, that's a good question. So the question was, are we going to turn in MATLAB code like to a server that I will then run, that will then run in the server and give you some feedback? Typically, I will have you just hand in the code along with the results they produce. So I'll have you hand in a typed version of the code along with the figures that it produces. So you'll be handing in on paper like everything else you turn in. You'll just be handing in your printout of your code. I don't think we'll be doing any kind of automated code grading. Frankly, for something this size, when the results you get from code are things like figures and numbers, but numbers can be a little bit off from other ones and still actually be correct. This just there might be slight problems. And so actually, the effort in auto-grading something like the level of code that we're submitting here, not because it's that complex code, just because the results depend more on solving a problem rather than on constructing a proper block of code. Because of that, it's typically easier just to hand in the code itself, and it's a small enough class where I can just spot grade them, and not spot grade them, but actually just check the code and try to point out. The hardest part is when there's a little mistake, and finding a mistake in all those lines of code can be the hardest part. But this isn't typically a class, so I can do that too. Oh, actually, I was watching the video the other night, and it's reminded me of one thing I have to say before this. So you might have noticed I tend to talk pretty fast. If you haven't noticed that, I tend to. So if you don't understand anything I say, please just raise your hand and then ask me what I just said. That goes for the video. If you see it on the video and can't understand what I'm actually saying, just send me an email and say, what did you say? Maybe like a link to the minute of the video where I'm saying something that you can't understand. As well as in class, just interrupt me and say, I couldn't understand what you said. I know I talk fast. It's not something I'm unaware of. So please, by all means, just jump in and ask. OK, so that's an interjection there that I wanted to add. Yes?
In this first class, you showed a power flow diagram from the sources of energy to the end user.
Yes.
In that block, and it was rejected energy. A huge part of it was rejected energy.
Yes.
So what does it comprise of, and do we have anything to use that?
That's more of a philosophical question, right? So this goes back. Let me take that briefly, but that goes back to this figure, right, of rejected energy. I'm actually going to get to that a little bit in class today, but what this boils down to is when they compute the energy of these things, like the energy of coal, they are tracking the actual amount of heat that coal will produce when it burns. Now, you cannot convert all that heat into electricity. For coal, we can't even come close right now. For other things, we can come closer maybe, but we can't do that. It's not just that we're being silly about it. It's just that we don't have the technology to take coal and generate electricity, extracting it perfectly optimally. So there is some energy here which certainly is just being wasted. For example, cars can be made more efficient. Heating can be made more efficient. Electricity transmission can be made more efficient. That is rejected energy that can be used. But some of that, they're kind of lumping all together. They're lumping all together with the fact that we just don't generate electricity with 100% efficiency. We're not even close, really. And so they're kind of lumping all that together. But actually, I'll get to that a little bit today in this sort of Energy 101 section here. Let me go forward. Yeah?
Does power market affect the production or the usage?
Does power market affect the production and usage? Right. Right now, power markets, as they exist right now, are on the production side. We don't think of typical power markets as having a cost for consumption. Consumption is treated as fixed, and you make whatever generation you need to make up for that. That's changing, certainly, with the smart grid, right? We're having things like demand response, which are actually the exact kind of flip side of that, where now actually the demand and the consumption is being made flexible and assigned a cost. We'll get to that a little bit more much later in the course when we talk about the actual optimization problems, though. OK, so let me get to a little bit of this problem. So again, we're going to use MATLAB here. This is a really simple bit of MATLAB code. If you're curious, you can run it. It does something kind of cool. It's unrelated to energy, as I said. But what it does is, what this code kind of line by line does, is it first constructs a matrix P. And P, as I said, is a matrix in R 3 by 2. So it has 3 rows and 2 columns. Right? That's just, I'm just writing down essentially what this piece of code does line by line as an illustration of you sort of need to know how to take ideas like this and translate them to code, or see code like this and understand the basic sense of what it's doing. And P here's a matrix that is equal to this thing. It's equal to 0, 0, 0.5, 1, and then 1, 0. The next line creates a big matrix X, which is in R to the 50,000 by 2, that is equal to all zeros, initially at least. The next bit is a for loop. So it iterates over I being equal from 1 to the size of x, and in fact, the first dimension of x. So this is this 50,000 number minus 1. So I in this goes from 1 to 49,999. And for each value of I there, it does the following. It sets the ith row of x. So this notation here, x I plus 1 colon, means we look at the I plus 1 row of x, and we look at all the columns of x. That's effectively looking at just the ith row of x. Sorry, the ith plus 1 row of x. And it sets this equal to 0.5, so half of it is equal to the previous value of x, or rather the value in the previous row, plus 0.5 times this, times p. And what this little, actually I should just maybe say it first, what this little statement there is doing is picking a random row of p. P has 3 rows, right? And so the way that works is you call this rand function. That generates a number between 0 and 1, a real valued number between 0 and 1. You multiply it by 3, so now it's a real number between 0 and 3. It's actually always going to be, it's never going to be 3 exactly. So you can think of it as between, because they're thinking of this as a real valued number, it's really going to be above 0 and less than 3. Multiply by 3, so now it's a number between 0 and 3 non-inclusive. And then we perform the ceil function. The ceil function rounds up to the nearest integer. So what this is doing here is it's picking a random number, 1, 2, or 3 with equal probability. That's all it's doing. And it's assigning x plus 1 to be equal to half of the last value of x plus half of some random value of p. And it does that for each of the columns. Sorry, each of the rows of x. And then at the end, we plot x as a 2D plot. So the first column of x is the x coordinate, the second column of x is the y coordinate. And that little b thing there just means we plot it in a blue color with a dot. So all these things, these are sort of, you don't need to know these exact function calls, by the way. But just being able to understand kind of the logic of what this is doing here is really about the extent of the logical kind of programming we're going to do here. You will need to know more function calls, and you can look those up as is necessary throughout the class. But you need to at least understand when you see code like this, what it's doing. Again, that's really sort of the extent of the logic. This is not going to be functional programming or anything like this. It's not going to be complex programming. Even though we're using MATLAB, which can be made more efficient by what's called vectorizing code. So if you write code in more of a matrix form, it can be more efficient. But for most of what we do in this class, if you want to, you can write everything out explicitly. You can do it kind of however you want, however explicitly you want to. It's just important that you understand the basics of how to do those operations. What was the question? Yeah?
At the size x comma 1, what does the comma 1 do with that?
So size returns the size of x, but x as a matrix really has 2 dimensions, right? So it has this dimension and that dimension. So size of x1 is the size of the first dimension of x, and size x, so that's equal to 50,000, and size x2 here would be equal to 2.
Okay, thank you.
So, and probably the most helpful function in MATLAB, by the way, is the help function. So if you're ever confused about that, if you didn't know what size does, for example, then just type help size. And same with all those. Help ceil, help rand, help plot. It will all tell you a pretty readable description of what that is. If you want even more, you can often type doc size. And that will tell you even more, pop up a new window with usually some examples and even more description about what's going on there. So that's it for MATLAB for today. We'll come across a little bit more MATLAB code later on, but that's kind of the basics of what you actually need in terms of understanding the programming concepts for MATLAB. The second thing that you'll need is some linear algebra knowledge. And this we will cover a little bit, as I said, in the review session on Tuesday. But really, it's not very complex linear algebra. We're talking mainly here about solving linear equations, manipulating equations in vector and matrix form. That's really the extent of linear algebra. You don't need to know that much about eigenvalues or eigenvectors. I think we might use them a little bit toward the very end of the course, but it's not going to be a major portion of the course. The biggest thing, frankly, is being able to write equations in matrix form. And actually, one of the hardest things for people, which is because it's never actually taught in a linear algebra course, is a little bit of intuition about how you take an equation that might be defined element by element, or defined in terms of sum notation. I mean, by I meant sum notation here, SUM notation, so like a sum from I equals 1 to n of some function there. Taking things like that and translating them into an equivalent matrix or vector form is really actually probably one of the more key points of the what you need to do in this course. But it's actually very straightforward. It's just people don't usually practice it. So hopefully actually through doing a lot of this stuff, you'll get some experience with that and with manipulating things into vector form. The actual sort of amount of linear algebra knowledge we need to know, I think, is captured by a problem like this, frankly. This is a pretty easy problem here. The question is, you have a linear system like this, and you want to say, what does x equal? Solve explicitly for x. Does everyone here know how to do that? Nodding heads. So the way you do this, right, is that, and I should also say, it's also important to know kind of the notation, like how we denote vectors. So I'll write things like Rn, this kind of double, or this kind of, I forget what that script is called, but that kind of type of R. I write it like this when I write it on the board. This means a vector in Rn, which you think of as a column vector typically. So this would be, if I say x is in Rn, that means x is equal to some vector like this, where I say x1 is the first element and xn would be the last element. To say a matrix is in A is a matrix in n by n, that means A is equal to something like this, an n by n matrix. There are n rows and n columns here. And the first element would be A11, first row, first column, up to A1n, then AN1, and ANN here. And these could be different sizes, of course, different numbers of rows and columns. But now for an equation like this, we have an equation like AX minus B plus X equals C. So how do you solve for X here? Yeah?
Add B to C.
So you move B to that side. So you have AX plus X
Then,
equals C plus B.
Then take out X. So it's A plus the identity matrix.
Right.
All times X squared.
So that's important, that little step you said there, the identity matrix. That's the one thing people screw up here. So actually, I'll even make it a little harder. I'll say 2x here. So what you'll often see is people write this. They'll write A plus 2 times x equals C plus B. And this is not valid here, because 2 is a scalar value, and A here is an n by n matrix. You can't add a scalar to a matrix. And in fact, MATLAB will let you do this. This is especially a really bad thing. This is actually a really, really bad fault here, because MATLAB will do this. What it will do is it will add 2 to every element of A. And that is not the solution you want. What you actually want here is A plus 2 times the identity times x. The identity is a matrix, an n by n matrix, where x, or really any matrix A, times the identity equals A. And you can do this on both sides also. You can also do this A times the identity. For four square matrices here, this would be. I'm actually, no, sorry, for any matrix here, though, these identities might be different sizes, depending on the size that's required for that. Yeah?
When you're adding in MATLAB, what again is the difference between plus multiplication and dot plus or dot multiplication?
Right, so we'll cover that maybe more in the MATLAB session, but if you say something like this in MATLAB, if you have two matrices and you say A times B, this is the matrix product of these two things, which we'll define in a second, but hopefully you guys are familiar with matrix products. We'll define next time just to make the definition explicit. A dot times B multiplies each element of A times each element of B.
Okay.
They're actually very different, because in this thing, A and B have to be the same size. In this thing, the number of columns in A has to equal the number of rows in B. You have these sort of the standard matrix multiplication rules here.
So is there no difference between plus or dot plus? Or because
There's no dot plus, because it's the same. It would be the same. There's no dot plus operation.
Thanks.
There are some review notes posted online about linear algebra, which you need to know. These are some I wrote a while ago for a machine learning course. And we're also going to, as I said, they're going to have this review next time. So come to that if it's been a while or if you're at all sort of want to make sure you can do. And in fact, I think the lecture today is going to be good for determining sort of what's the right level. So let me go on and start the next lecture.
Will you show us what that code does? What it draws?
You can run it yourself. You can just copy and paste directly out of that thing. It's cool to think of actually why it does it, which is not at all obvious. All right, so let's jump into the first unit of this course, which is, as I said, the course is organized in terms of 3 overall units. The first is going to be about machine learning for energy systems. This is about using data to make predictions that might be hard to do from physical principles. The second is going to be about electrical power systems. So how do we use physics to model what's going on in the power system and in a power grid? And the third is going to be about control. How do we put these together, predictions and known physics, to actually control the system and make it behave optimally? Now, the first lecture, I'm calling this machine learning, and I think people can call it machine learning, though this linear regression predates machine learning, the term machine learning, by about 200 years or so, approximately. So we've co-opted this term now, us people in computer science here, but this is by no means specific to computer science, the computer science version of machine learning. This is a very, very general set of algorithmic and mathematical modeling tools here that you use in a lot of places. Before that, though, I actually want to just present some motivation and then also present a really kind of brief background about energy. And I have a little demo that makes this even kind of fun here. So I think I kind of set this motivation before, but let me sort of motivate some of the questions we're going to focus on a lot during this unit on machine learning. And that is, how much energy will we consume tomorrow? And by we, I mean whatever, maybe me, maybe all of Pittsburgh, maybe all the US, whatever. How much will we consume tomorrow? It's easy to know what we're consuming right now. You can do that with kind of physical measurements in a lot of different places, actually. And but it's hard to know what we're going to do tomorrow, right? That's kind of humans are uncertain. I don't know what I'm going to turn on tomorrow. If I'm going to turn on my toaster at 2. Probably won't turn it on at 2, actually. I can say that with some confidence. But I mean, I'll turn my toaster at 8 in the morning, right? I don't know. Maybe I will, maybe I won't. I have that choice, I would think, right? So how do you know how much we're going to consume tomorrow? It's hard to really estimate this, right? It's hard to sort of write a program that could use a mathematical model, well, an a priori mathematical model, kind of like a physical mathematical model, to do this. But as I said, we have lots of data on these things. We can observe a lot of previous days, see how much energy was consumed by me or by the entire city of Pittsburgh or by whatever unit you want to look at, and try to use that past data to predict what's going to happen in the future. That's the basic idea here. It's a very simple idea. Use the past to predict what may happen in the future. The assumption being the future is going to be like the past, I guess. So before doing that, though, I'm using the terms energy a lot, and I'm going to use the terms energy and power a lot, and we're going to go through this in some detail when we talk about electrical power systems, because there you need a little bit of knowledge about voltage and current and all these kind of things. But before I even define that, let me just define the basic units of energy that we're going to use here, just so we are speaking a common language here. Energy, in its most basic form, I guess, or the definition of energy, is just the ability to do work in some sense. Of course, that's not really a definition, because I'm not just loading the definition into work, right? What is work? So I'm going to really define energy as applying a force through a distance. So what I mean by that is this eraser here, and I probably can't see it from the video, so maybe that's no good, but I'm doing it on a table. I'm pushing an eraser across the table. This eraser here requires some force for me to move, and I'm moving it some distance. That required some energy to do that. And in particular, a typical unit of energy, which is a joule, is 1 Newton, which is a unit of force. That's how much force I'm exerting there. Really, I'm exerting force here just to counter the force of friction that's pushing against me. I am exerting a force of some amount of newtons through some distance. And a joule is defined as 1 Newton, unit of force, times 1 meter, applied through 1 meter. Now, that's not really very intuitive, but we'll get to that in a second. And by the way, a Newton here is a kilogram times meter per second squared. So the Newton's law is F equals ma, so force equals mass times acceleration. So you have kilogram, which is mass, times acceleration, which is a meter over a second squared.
Is meter not supposed to be squared?
Meter is squared in the units of joules because force is kilogram meters per second squared, and then you're multiplying by meter again.
Oh, okay.
Now, that's not very intuitive, so I'll get into a sec what that actually means. Because our understanding of energy is not really so much of the definition, but actually what it really corresponds to in the physical world. We can get a really good intuition about energy because we use it all the time. Power, importantly, and I think this is, everyone here knows this, but it's important. Everyone sort of emphasizes this at the beginning of a class on power or energy. Power is a rate of energy use. All right, so power is 1 joule, and the most common unit of power is a watt. And a 1 watt is 1 joule per second. So if I am exerting doing a joule of energy to move this thing around, and I'm doing that constantly, then each second I am using a joule of energy, so I'm exerting 1 watt of power. So when you say something like watts or kilowatts, you would never say something, if you're talking about how much power something's using, it's using a kilowatt. It's not using a kilowatt per second. It's using a kilowatt of power. It's using 1,000 joules per second. So this becomes fairly intuitive pretty quickly, but just know that people will sort of, power people always are, they want to be very specific, and if you say things like using a kilowatt per second, then they don't like that. Rightly so. But the problem with this definition, as I said, is it doesn't really capture intuitively what energy means to us. I don't really get an intuition for energy from this definition here. And the thing about energy, which makes this nice, is that energy takes on many different forms which we are very familiar with. For example, one of the most common ones is kinetic energy. The form, and I'm actually using, so let's see, so I'm writing here energy, a bunch of equations for energy defined in terms of different quantities. These formulas themselves are not important at all. I'm just writing them just to know that there is an actual formula for these things. But what's important is just to understand the different forms energy can take. So one of the most common is kinetic energy. That is the energy of something in motion. Something has mass and is moving at a velocity. It has energy. The energy is equal to 1/2 times the mass times the velocity squared. We're not going to worry about what is it moving relative to. We're just going to think of a fixed frame. We're talking about Newtonian physics here, not anything more complex than that. So just think about moving relative to some frame that has energy then. Another kind of energy which is very common is potential energy. And oftentimes in physics classes, the first time they'll sort of talk about how potential energy can be transformed into kinetic energy, right? So if you pick something up, it has potential energy now because I can drop it and then let it fall, and now it's moving. So it has some energy now, and now it has transferred from potential to kinetic energy by dropping it like that. Again, the formulas there are not really important. It's mass times gravity times how high you pick it up. Thermal energy is also an energy. This is, I'm going to be very careful here because people use definitions of heat and thermal energy differently. Those are actually different things. And temperature, these are all actually very different things. But we're not really talking about the physics here, so I'm not going to use them too carefully here. I'll sort of talk interchangeably about them. If I do, I'm sorry for the more physically sort of rigorous people here. But thermal energy is equal to the number of molecules in a substance moving around times 3/2. The 3 there comes from the fact that we're living in a 3-dimensional world. So in 2D, there would just be 2/2, I think. Times K, which is some constant, times the temperature of the system. So that, again, that's sort of in some sense just offloading the definition to what temperature means, but temperature of something really corresponds to energy, right? Because This is really just kinetic energy at the molecular level. When you heat something up, the molecules start bouncing around each other very quickly, and that is energy. We experience that as heat. Electrical energy here, that's defined as voltage times the unit charge. Really, this is a horrible, not a very good definition. The better definition is what voltage is. Voltage is energy joules per unit charge. But you can also flip it around and define energy in terms of voltage and charge. Electromagnetic energy, this is light, essentially. And it has to do with the wavelength, the frequency, the wavelength of the light, times a constant there. Chemical energy, this is energy used in a fossil fuel, right? There's energy innate in that because we can burn it and release heat. Or really, a lot of things you can burn and release heat, fossil fuels being one of them. There's a lot of definitions for this because it depends on the different material you're talking about. So I didn't put one clean definition. And finally, nuclear energy is the well-known E equals mc squared law here. So again, lots of different forms of energy. And the interesting thing between all these things is that energy can be transferred from one form to the other. So I'll give a very simple example of transferring potential energy here to kinetic energy by dropping something. But really, there's a lot of ways in which energy can be transformed into other forms of energy. In this class, we're going to talk about using energy or taking up energy or using them at power. Of course, the conservation of energy means you can't actually use energy in some sense. It is always conserved. I guess maybe except depending on your definition, whether or not you treat the nuclear systems as conserving energy or not. They are still, it's just energy in mass is being conserved there. But when we talk about energy being used, what it really means we're transferring energy from a form that we can get some sort of useful service out of into a form that we can't really get a useful service out of. So for example, at a power plant, you may burn fuel to produce electricity, and that sort of wasted energy that we're using. I mean, some is transferred into electrical energy here, but other is just transferred into heat. And we're saying we've kind of used a certain amount of energy, and then eventually, we use the electricity for something, and all goes to heat. Everything goes to heat in the end, it seems like. But when we say we use that amount of energy, what it really means we transfer it from a form that we can use, like electricity, to a form that we can't use, like heat. Now we can use heat. Heat is good a lot of times. Sometimes we actually want heat, but oftentimes we don't want heat. And for a lot of useful work that we do, we actually need heat to have a very high temperature differential. So if heat's only a little bit hotter than the air around us, it isn't really that useful for us, unless you just want to warm up the room. Other than that, there isn't really much use for it. You can't convert it back into their forms very easily. That's what we mean by using energy. We're really just increasing entropy. Okay, so this is a little diagram, though, about some of these types of conversions you can do. So a lot of things can be transformed to thermal energy. Nuclear, there's fission and fusion that will release huge amounts of heat. You can, thermal stuff will expand, and that will, so a set of molecules that heat up will actually try to expand, and that can actually exert force against something else and turn that into mechanical energy. Thermal energy, actually, things get hot enough, they start to radiate and produce light. And so this is not a complete graph by any means, but it is a sort of suggestion of some of the ways in which to transform one source of energy to another force. And to emphasize this, I like to give a little, let's see, where's my box here? I like to give a little demo. This is not really called a demo, but it's a illustration of just how crazy this can get. From the simplest thing that we do every day, which is turning on a light bulb. So let me turn on a light bulb. There's not going to be any surprise here. But what I'm going to do is plug this thing in and just turn on, see if you can see me. Yeah, I'm just going to turn on this light here. Okay? So the question is, what just happened in this little graph? Yeah?
We use resistor to electrical energy to.
Right. So that's the last thing that, well, it's actually, so what happened? We use a resistor to do what? Electrical to what? Right?
Electrical to thermal.
Uh-huh. And
we heated up the resistor and then
yep.
Produce heat energy and electricity.
It doesn't produce any electricity, I don't think.
It uses electrical energy to produce.
Right. So it went from electrical to through a resistor to produce thermal. Then it got hot enough, and it was the right material, such that it radiated light, electromagnetic energy. That's only part of the story, though. What really happened is that a long, long time ago, this is probably where most of this energy came from, actually. A long, long time ago, some material in the sun fused together, and that released a lot of heat. Right? These atoms got really hot. Sorry, yeah, they got really hot. Things fused together, released a huge amount of energy, heated up these elements. So we're thermal energy now. These elements got so hot, hydrogen and heavier elements got so hot that now they're oxygen or other elements after you combine them. They got so hot that they radiated light from the sun, right? Going out in every direction. Some of that light hit the Earth, and through photosynthesis became chemical energy in plants. That was long time ago for most energy we're talking about here. That energy, maybe these dinosaurs ate these plants or whatever. They died. The plants or the dinosaurs, whatever, died, covered up by a lot of dirt over a long period of time. And then we dug them up as fossil fuels, shipped them to a power plant and burned them, put them on fire. That also released heat, right? In fact, what we probably did was we burned some stuff up to heat up some water. This water got moving really fast. It expanded to turn some gears, passed through some fans in a turbine, and started these fans moving. That moving turbine was hooked up to a big magnet that spun an electrical field, and that created electricity. And then we hooked it up to it, and then it traveled from the power plant across the transmission lines to this outlet right here. Electricity traveling is not quite the right notion, but the electrical potential was influenced by what happened there, down to this outlet here, where we heated it up again, and that got hot enough that it released some electromagnetic energy. Yes?
Do any of the generators use combustion like an engine with pistons or anything?
Yeah, so some gas turbines will directly expand gas to directly do work on the turbine itself. So they'll just burn gas directly. It's actually the same exact process, though, because you're still heating up a chemical to expand that generates heat, which expands, which causes kinetic energy.
Which is usually used for which?
So there's a lot of variation here. A lot of the coal plants and such will actually heat up water, and some of the sort of more the slower ramping power will heat up water. Because it's actually not that inefficient. I mean, nuclear plants, for example, just drop a nuclear rod into a vat of water, and that's not actually that inefficient. It sounds crazy, but that's how we actually get water from it, right? That's how we actually get energy from it. Some fast-acting, they're called open-cycle gas turbines. They directly use combustion to spin these things, but they're both.
Okay.
Yeah.
And those open cycle use just dense natural gas?
They just use natural gas. I'm not sure the density that they pump it into, but they use natural gas. They just light it on fire in the turbine itself. So that's this little path here, right? We're going from here to like this little roundabout way to actually produce our light. Now we can do another thing here, which is swap out this incandescent bulb here for an LED bulb. These are about 5 times more efficient. So it's the same amount of lights produced. It's an LED bulb, 5 times more efficient. In energy, 5 times more efficient is about as good as you can get, right? If we could make all our consumption 5 times more efficient, that would be incredible. This is a huge deal here, going to LED bulbs. And what we've done on this picture is essentially cut out one step. What LEDs do is they directly transform electrical energy to light without going through heat. They release some heat, but the actual mechanism inside is using a photoelectric effect to, the other way. That's electromagnetic too, that's in solar panels. It's using a physical property to directly convert electricity to light. And we've increased by 5-fold, and we've, just doing that, bumped up our efficiency. By cutting out one chain in this graph, we've bumped up our efficiency by 5-fold. Another thing we can do is just open a window, right? That also would be a nice thing to do. That goes directly then from nuclear to thermal to electromagnetic. And sort of sad I have the windows closed here because if they're open, then the video quality isn't very good. So I'm trying to release it. But unfortunately, by doing that, I'm using all this light here, which is a horribly inefficient way of actually producing light, given that we have a free source standing right outside. It goes through many, many fewer chains here. Anyway, that's an aside. That's all I'm going to say about energy for right now. Again, this was sort of a little silly kind of demo here. This was just a sort of a silly little illustration of some of the way energy is converted and some of the uses of energy. We will talk much more, in much more detail about electrical energy in particular and how we control and model that. But it's important to know that energy really is all these different things. We use all these different forms of energy. And so when we talk about using less energy or conserving energy, all this kind of stuff, we're talking about how can we make better use of these different forms of energy. So now let me jump into the last bit, which is really using machine learning to, and linear regression specifically, to predict how much energy we will use. And I'm going to talk about how much electricity we're going to use. So shifting gears now to something a little bit more concrete. And this is the problem of predicting how much electricity, even, I'll even go from energy to electricity, how much are we going to use tomorrow? This figure here is a plot of the amount of energy used by Duquesne Light. Duquesne Light is the utility servicing the Pittsburgh area. Here is the coverage area of Duquesne Light. So it covers Allegheny County and some of Beaver County. We're right here. It's mainly Pittsburgh, though. That's where the majority of their energy goes to. This is a graph of 3 days, 3 different days of the year, how much power was consumed each hour. Now, I'm already kind of doing it there, kind of talking informally. Power is not really considered right. What we're doing is consuming energy in some sense. When I say power, the average hourly demand, what I mean is if you look at the actual instantaneous demand for that whole hour and average together, that would be the average hourly demand. So if you multiply by seconds here, you'd get the number of gigajoules of energy. Number of seconds in an hour, you get the number of gigajoules of energy. But we're going to talk typically about, a lot of times you'll look at power consumption or people using energy, and I'll use the words power consumption pretty liberally. I will think, it's important to be specific about what you mean, but power consumption is a pretty common term. So I'll use that and energy consumption for the most part interchangeably. If I ever make a mistake about something that really isn't correct, right, then speak up and address me. But though that one I'll use interchangeably. And what this shows here is 3 different days, February, October, and July, and the amount of power, the average amount of power that's consumed each hour of the 24 hours of the day. And what you see is that it follows kind of a pattern you'd expect, right? In the middle of the day, there's a little bit more usage. People are awake. People don't use much power at 4 in the morning. Not many people are awake right then. And so you expect people to use more power in the middle of the day. In the summer, in particular, there is a lot more power consumed right in the late afternoon. And there's a big spike in power in the afternoon. This corresponds to the main source of consumption in the summer is air conditioning. Not main source of consumption. A very large source of consumption in the summer is air conditioning. That's actually probably the major reason for this big shift here. It doesn't start at 0, so it starts at 1 here as the baseline, so it really goes down to here or so. In the winter, say February, it looks a little bit different, right? It's actually power kind of drops off in the middle of the day. This is because, well, in the winter it's kind of the opposite, right? We need heating, but we need heating most when it's really cold, and that's more at night and in the morning. Now, heating is not that much produced by electricity, though there is some produced by electricity. Heating is typically gassier, so it's not showing up as the main source here. But there are also things like lighting. Lighting is much more common in the winter at the 2 ends of the day because that's when it's dark. You don't need all the lights on when it's not dark. And this other October 10th falls somewhere in the middle here. So this kind of corresponds to what you would expect. There's higher consumption in the summer when when you have the middle of the day, when you have air conditioning, you need to cool things off, and in the winter it's a little bit different. So let's look at one problem in particular. Let's actually think about just forgetting about the demand at every second tomorrow, or every hour even. Let's just try to predict what the highest demand is going to be tomorrow. And I'm doing this just to sort of to simplify the problem a little bit. I want to know not from just what's our power going to be every hour tomorrow. I just want to know what's the biggest amount of power we're going to consume tomorrow. Just to make it a single number we're predicting rather than 24 numbers we're going to predict. And the key idea here, and the key idea really of things like regression, linear regression, and really machine learning in general, is that we don't quite know what's going to happen tomorrow. We don't really know that. But we might know some other information about tomorrow, or about whatever situation we're trying to predict, that will give us some insight into how much power we might use, or how much whatever we're trying to predict there might be. And a simple example of this is, let's say that we know what the temperature will be tomorrow. Remember, I told you before that in the summer in particular, the temperature really affects consumption, right? Because the higher temperature, the more air conditioning we need, and that causes us to use more power. Let's ignore the fact right now that temperature actually is also a prediction. It's just a weather prediction, right? So you're just using some models to predict that. Let's go ahead and assume that those are pretty good models, actually. And they have some physical properties, some data properties. We're not going to worry about that. Let's assume that someone tells you what temperature will be tomorrow. Can you use that to predict the most likely peak demand tomorrow? And one way to think about that is let's just plot the data that we have so far. Okay, let's plot all the data we have of what the high temperature was, and then how much energy was actually consumed. Okay, that was a question? Okay. And as you can see, it sort of follows the pattern you expect, right? For higher temperature, there is more consumption here, right? Which seems very, very reasonable. Now, I don't think using just this, and you can actually get this from the figure right here. You don't, and I should say these are real dates. This is the peak consumption as recorded by PJM. That's this organization that logs how much that organizes the distribution and generation of energy, and will log, for example, how much power the Duquesne area consumed every hour. So I got the data from PJM. I also got weather data from a weather site called Weather Underground. You can download, sort of scrape the data there in a freely available format. So I did that for a couple of years, and I plotted in the summer months only. I'm only showing summer months here. So this is June through August. We'll come back to that in a second. But in June through August, for a couple of years in Pittsburgh, I plotted the peak hourly demand, so the highest point of demand during the day, and then what the high temperature was that day. And there's a pretty good correlation here, right? You can see that with higher temperature, we actually do use more energy. I should say that predicting peak demand is actually a very important problem in its own right, because oftentimes you'll need to provision your generators to keep up with the peak demand tomorrow, right? You need to schedule enough generation, not for the average demand tomorrow, because it's not good if you can provide the average demand. When the demand goes a little higher, you need to be able to satisfy that. So knowing the peak demand tomorrow is actually an important problem in and of its own right. Now, I would say that I probably actually can't do a perfect job of predicting this given just the temperature. And I can say that because even looking at past data, there are times when the temperature is virtually the same and there is some spread of how much power people actually used. So I'm not likely with just this input to be able to predict this perfectly accurately. But I can do maybe a reasonable job. I can get a pretty good, maybe average estimate of what we expect to happen tomorrow. And though we won't talk about it here, you can also do things like predict how much variance there might be from that as well. And really that corresponds to essentially drawing a straight line through this data. Not very complex here, right? You can imagine this. You can say, okay, this is kind of like a line, right? Sort of a linear relationship here. Let's just draw a line through it. This is what we're going to call a linear model, a linear prediction model. What this really is mathematically is that we have two numbers. I'm going to call these theta 1 and theta 2. And we're going to predict the peak demand tomorrow to be theta 1 times the high temperature plus theta 2. And so in this graph here, theta 1 is the slope of this line, and theta 2 is the intercept of the line. So if you went all the way to 0 high temperature here, you would have the theta 2 would be that value, and the slope of the line is dictated by theta 1. So all we're doing is we're just taking our data and drawing a line through it, and we're calling that a model. And it's important to understand that this is a model, right? Because this line here, we can use it to make predictions. I'll talk in a second about how we actually go about determining precisely that line. But this line is a model is a predictive model. And the reason for that is we can use it to make predictions. So if I ask the question, what will the peak demand be tomorrow? I can answer this by saying, well, what's the high temperature going to be tomorrow? And again, that's also a forecast, but whatever. I'll just say that I look it up on weatherunderground.com, and I say what the peak demand is going to be, and then I just take that number, say it's going to be 80 degrees, actually probably pretty reasonable for tomorrow, right? And I just plug that number into my equation here. Right? Remember, this equation says predicted demand equals theta 1 times high temperature plus theta 2. So I take 80 degrees and I plug it into that model. And that gives me a prediction. It says the predicted consumption, peak demand, is going to be 2.19 gigawatts. This might not be completely accurate. As I said, if we made the same prediction in previous days, we could be off sometimes, but on average, we'll be pretty good. And that's the basic idea of a really kind of, this is the core idea of machine learning. You build some model that fits your data, that given past examples of data will track some output, and then given a new data point, you just predict, you plug that data point into your model, and that gives you your prediction. So you probably, a lot of people, actually, who here has done linear regression before? Has used it before? Okay, so this will probably be a review for a lot of people, but maybe not everyone. So let me formalize this a little bit, though, because linear regression is described in a lot of different ways. And I think oftentimes it's described as like projecting your data onto a line, what's the best projection. But I'm going to talk about it a little different. I'm going to talk about it in terms of an optimization problem. And so I think it's really important to understand what that optimization problem is and how do you get linear regression out of that. And then we'll go from there to talk about sort of more complex models we can do in the same kind of framework. But first, I'm going to just describe some notation. I should say, I'm going to try to go slowly here, even though I think a lot of people know this already. I think it's important to kind of get the formalization of this type of problem, too, because this formalization is actually going to be used in a lot of machine learning problems. So we have a couple things. First of all, we have an input. An input is going to be written as xi being a vector in Rn, where I here goes from 1 to m. And what this means is we have an n-dimensional input vector, an n-dimensional vector describing the input to our system. In our case here, though I'll talk about a more complex case shortly, not today, but pretty soon, our dimension of n is 1, right? Because our input, we have one input, and our input is the high temperature. So in our case, n equals 1. M here, m is the number of data points that we have. The number of data points we have. And so if we have data from 300 days before, then m would be equal to 300. Our output, and this is actually a very important point here, xi here refers itself to a vector. Oftentimes, the rest of like a vector is x, and then xi will refer to the ith element of x. That is not the case here. Here, xi refers to an entire vector. It's a little bit confusing because in our case, the first time, x is actually a one-dimensional vector, so it's really a scalar, but don't worry about that. X in general will be a vector, and xi is itself a vector. If I want to sub-index into an element of x, what I would write is I would write the following. I would write xi, then put brackets around it, parentheses around it actually, sorry, parentheses around it, and then say sub j. So this would be the jth element of this vector xi. I could do it in a few other ways too, but this is some notation I'll use a little bit. Though typically I try to, because it's kind of a little cumbersome here, the goal of a lot of notation is to write it in a way where you don't really need to do this kind of stuff. So a big benefit of linear algebra notation is that we actually oftentimes don't need to do this kind of thing. And so we typically will define everything we need in terms of vector operations. So things like inner products between different vectors. Okay, so secondly, the output of our system is going to be yi. And yi is always a scalar, sorry, it's not r to the n, it's just yi is a scalar value. A one-dimensional vector, just a number. And in this case, y is a number. In other cases, what we're trying to predict might be like a category, right? We might either be, is this a yes, no? We might be trying to predict a yes, no response to a question. If y is a real value number, we call this a regression problem. If y is a discrete valued quantity, we call it a classification problem. We'll talk about classification in a second, but y here being real value means we're talking about a regression problem. In our case here, y, again, it's a scalar value, and it would be the peak demand for day 1. The next thing we have is some model parameters. These model parameters, which I'll write as parameters, which I'll write as theta. Theta is going to be a vector in r to the k. So we have k different parameters here. And for example, in our last model here, we had theta 1 and theta 2. So k was equal to 2, right, which corresponds to the slope and the intercept. K does not always equal the same as the input dimension. In fact, it does not have to at all. And we'll talk about why that is the case. But we have a certain number of parameters to describe our model. In this case, it's one more than the input dimension, but using notation we'll talk about shortly, this can be different. And finally, we have a predicted output. So the predicted output is our prediction of what we sort of think the output for the ith example is. So we have predicted output, which I'll call y hat I. This is going to be in R. And this is our model's prediction of what this output is. And I'll actually define what this is in a second, a little more formally. Well, not formally, but a little more concretely. But for now, just think of y hat I as being what we think. And remember, what we think, depending on our model, is not always the same as what the output really is, right? So if we have this data, and we have yi, say, for this example here, is, something like 1.75, our prediction is up here. So this value would be the prediction for this example. And this value, I should say, this value here, 2 or so, would be the prediction according to our model of what this is. And this value here is just the actual output itself. Not always the same. And we'll talk about quite a bit later, you don't always want these to be the same, because if you're fitting all your data exactly, that model might be very, very specific to your actual data, and it might not be very good at making predictions then. So sort of store that away for later, because then later we'll talk about that more. Okay, a couple more definitions here. For convenience, but really this is an important point, I think, to sort of think about how we define these models, we're going to define something called a feature vector and a feature function in particular. So features are defined as follows. They're defined by a function phi. And essentially, is everyone familiar with this kind of notation here when I write phi being a function from Rn to Rk? What this means is that phi is a function that takes as input vectors in Rn and outputs vectors in Rk. So in particular, we can take our inputs, feed them into this function phi, and get as output a k-dimensional vector. I'm not saying anything for right now about what this function actually does. I'm just saying there exists some function here. For example, in the task above, we can define a function that takes as input xi. So phi, for example, would be the function that takes as input xi, and returns this. So in our case, this would be a take a one-dimensional vector input, because our input is just one-dimensional. It's just the high temperature that day, and outputs a two-dimensional vector. This is a very simple two-dimensional vector. All it does is it takes our input element, uses it as the first element in that output matrix, and that output vector, and then the second element of that output vector is just equal to the constant 1. So why on earth would we want to do this? Well, this notation makes it a little bit easier to define these predictions a little bit more uniformly. So using this notation of features, we say that our predicted output, I think I'm actually kind of losing, I want to make sure that I can get this all on the, okay, now I have some space there. All right. Using this notation here, we're actually going to always have it be the case that our predictions, our y hats here, are going to be the following form. Y hat is going to be equal y hat I. Y hat I is going to be equal to the sum of all the parameters times the corresponding elements of that feature vector. It's going to be equal to the sum. And remember, there are k different elements in the feature vector. So the sum from j equals 1 to k of the kth element of theta, sorry, the jth element of theta. Again, this is some a little bit abusive notation here, because when theta does not have a subscript like this and it is a vector, I will use subscripts to index into that thing. So theta j here means the jth element of theta. Xi does not mean the ith element of x, because xi itself is a vector. So this is just sort of life in some respects. You're going to have to get used to these kind of things when you do matrix and linear algebra notation. But it's going to be equal to theta j. So our prediction is going to just be really a linear combination of our features, where the coefficients of that linear combination are given by our parameters. It's going to be equal to theta j times the jth element of phi of xi. And for the sort of those that know the linear algebra notation, this is written as, can be written without a sum, without too many indices, whatever, as just theta transpose times phi xi. And this bit right here is really important. Not this bit here, but this bit here. Throughout the entire course, y hat I will be equal to this. The inner product of our parameters and the feature vector. Now, actually, everyone sees that why these two are the same thing, right? This is this. So an inner product takes the corresponding elements of each vector, multiplies them together, and adds them all up. So this is just by the definition of matrix multiplication, this expression here is equal to this sum. So that's our definition of inputs, outputs, predictions, and features, which is really all you need to have. This is sort of, definitionally, this is kind of it. This is all you need to know to do machine learning, or to at least have the framework for computing predictions in machine learning. So let me talk about one more thing, though, which is the notion of a loss function. So in some sense, these things, all that I talked about here was just definitions for what a model is and how you make predictions from a model. I didn't talk about what makes a good model. Right? Predictions can be, by notation, anything. Because I can choose whatever I want for my parameters. You know, have 1,000,000 in each value. That would probably be not the best model for predicting this thing, right? Because I'd get predictions that were pretty bad if I did that. If I chose random elements for my parameters here. So the question is, what makes a good model? And there are a lot of ways you can talk about this, and in fact, we'll talk about it. This is actually a pretty complex question, because there are these things like, well, is the model too specific to data, or is it not fitting it well enough, all those kind of things. But for the time being, let me state one kind of intuitive criterion for a good model, and that is the predictions should be pretty close to the actual outputs. Maybe I won't even say pretty close. They should just be close, right? We don't want to make them far away from the outputs. We don't want to try to make them intentionally bad in some sense, right? So we would like to have a model where our predictions, remember the predictions are given by this thing, by our parameters. So the predictions are really functions of the parameters. Our predictions better be close to the actual outputs. And we want, in some sense, to predict the parameters that makes this as close as possible. Though we'll formalize this much more in a second. I can say, I don't think I'm going to get through all of linear regression today. So I mentioned at the beginning of class that we'd have a review session next time. I will still do that, but I will first get through all of this, because I want to go through kind of the applied, what you use linear algebra for, before spending a lecture boring you all with the details of linear algebra. So we'll cover actually a lot of the cool stuff, I guess, next lecture. But anyway, we'll define loss functions for now. Maybe stop after that before it gets too involved. So we want our predictions to be close to the true outputs, and we're going to measure. But the question, okay, again, is what does close mean? Well, for a one-dimensional thing, you can sort of say, okay, close means that they have to have the difference can't be too big. But again, how do you measure big? These are actually not obvious questions here. How do you measure the difference between two things? Remember, we're taking a model here that should sort of have all the y-hats be close to all the y-hat i's be close to all of them. So we're talking about this, we want this for all I. So how do we measure that? I mean, what if one model has some of them close and one really far away, and the other one has come all kind of a little bit farther away? Which model is better? That's hard to kind of say unless you have some formal notion of what you mean by this being close to that. And what a loss function does is a loss function quantifies what we mean by closeness. So in particular, and I think part of the disadvantage of using a video is that I do erase the board a lot. So I'm going to erase stuff. Hopefully that's okay. You can look back at what this is. You hopefully can write it down. And if I start erasing something and you haven't written it down yet, just let me know. I'm going to erase this now and write this loss function now. So maybe I'll sort of write again sort of what's important here. Remember, we have our output, yi, and then we have our prediction, y hat I equal to theta transpose phi xi. Incorporates pretty much everything we talked about just now. And we want this to be close to that. So an example, which is the most common example, though by no means, it's common, really, I think we have to be honest about ourselves. It's common because we have a nice solution to it. It's not used because we think it's actually a good measure, though it might be a good measure in addition to that. A very common example for a loss function, and I should say a loss function then is something which compares these two things, right? So a loss function takes as input r by r. Sometimes, so really, you can also write this as a loss function takes a value in r2, but really, I'm going to specify this as a loss function taking two separate inputs, each of which are a real valued number, and it outputs a real valued number. And in fact, it outputs a positive real valued number. Loss functions have to always be positive, and we denote that as saying a number r subscript plus. So a loss function is something that takes a prediction, a true value, and outputs some number, which is 0 if they are close together and really big if they are far apart. A common example would be the squared loss function. So the squared loss is defined as loss of yi and y hat I is just equal to, well, you just take their difference. Of course, the difference itself is not a very good function, right? Because that could be negative, so that does not work as a loss function. We take the difference, though, and we square it. And that's our loss function. As I said, this is not the only one you could use. You could also might use this one, right? Take the absolute value of the difference. I don't know why there would be any reason to prefer the first one over this one, except, again, the fact that we happen to be able to solve the squared loss function nicely in some sense. We can kind of come up with a nice vector or a nice matrix form for it. Sorry, a nice form that uses matrices to compute what that is, what the solution is. So we'll talk about these other ones later, probably class after next. But squared loss is a pretty nice thing to start with. Right, and it sort of satisfies what we want, right? Because if they're the same, this will be 0. So if all predictions are exact, these will be 0, which is good. You know, that means we're getting predictions exactly right. Again, modulo the fact that we don't want too complex a model to do that. And if these are really far apart, then this is a really big number. So, you know, we probably shouldn't choose parameters that give us an enormous loss. So we want things to be pretty close to their actual value. Yeah.
You said because it's easy to solve with matrices. Are you solving the summation of the squares just by multiplying by the transpose?
It's not going to be quite that. We'll talk about how you actually solve that in a second.
Okay.
We probably won't get to it today because I actually want to spend a fair amount of time doing that, because that's kind of actually a nugget of what will come up again and again throughout this course, sort of this way of tackling a problem, formulating it as an optimization problem and solving it. But let me just define what the problem is, maybe. So we want to find now parameters that make this thing small for all our outputs, or all our examples, right? Remember, we have m different yi's here, and n different corresponding xi's. We want these to be small for all of them. And the way we measure this is through some more notation here I'm introducing, but the sum of loss functions over all our examples, typically called a cost function, and the cost function, which we'll call j of theta, this is equal to the sum from I equals 1 to m of all our loss functions, yi, y hat I. Note here, I will sometimes omit dependencies. So y hat I clearly depends on theta. So this whole thing is a function of theta. But I'm omitting that here because it's just kind of inconvenient to write y hat theta or y hat theta x comma x every time I do that. So you have to just sort of keep in mind that these things, this itself is a function of both the features, the input, and theta. I will typically write it only in terms of the, only emphasizing the parameters that are really important to us. So j of theta is defined as the sum of all these loss functions, which for the example of squared loss, writing this out a little bit more explicitly, this is equal to the sum from I equals 1 to m of theta transpose phi xi, that is just our yi hat there, minus yi squared. Because this was our squared loss function here. And now we can write our objective formally as what's called an optimization problem. We'll come up with optimization problems a lot in this course, but this is a very simple one. What it says is we want, and I'm going to write it this way, I'm going to write our optimization problem as we want to minimize over theta. So when I say minimize and have a variable below it, it means I am minimizing over this variable here. We want to minimize over theta, j of theta. What that means very intuitively, again, is we want to pick those parameters that make this cost function, the sum of all the losses, as small as possible. That is the objective for our model fitting procedure, which in this case is called, among other things, the least squares model. Because we're finding the theta that makes this sum of squares as small as possible. Now, how we go about doing that is a little bit, trying to see if I have time to how much I want to get into this. Maybe I'll just, I think I'm talking about, okay, maybe I'll do this next little bit, but I won't talk about how you actually do this. What I'm going to do first, though, is write this thing, sort of the first step to a lot of things we'll do. We're going to write this in a slightly different form. If we were to write it like this and try to, just solve for theta like this, we clearly could do it. Find the best theta like this, we certainly could do it. It's actually exactly equivalent to what I'm going to do. But a lot of these procedures of optimizing variables and finding the best variable to fit some model here is a lot easier to do if you use matrix and vector notation. So I'm going to take this equation here. I'm going to put it into vector form. I'm actually thinking again because I might actually have that be a prelude for what I'm going to do next time, because that in and of itself is actually probably one of the more key points that you'll have to get comfortable with. Taking equations like this, these have sums, they have inner products here, they have squares. You want to take all of this and you want to put it into a very simple form. And so next time in class, we'll do two things before our review. We'll first put this equation into a form of matrices times vectors minus other vectors, but something where we don't have any sum involved here. We'll write it just in terms of a matrix equation, vector equation, and what's called a norm of that vector equation. That's what we'll do first. The next thing we'll do is we'll talk about how you can solve this problem, which is finding the best possible value of theta using some very simple calculus. And really, calculus, people here have all had some background in calculus, right? You actually, all you need here is to take derivatives. It's not even integral calculus or anything. So this is really simple calculus. But you have to apply it to vectors and functions of vectors. So it looks a little bit more complex, but really it's not at all. Because this is a vector here, we need to use some calculus that uses multidimensional inputs and outputs to functions. And so we're going to talk about that a little bit. But that really is sort of the extent of the calculus you will use in this course. So next time, as I said, we'll do this first. We'll show you how to solve least squares. Again, I think this is sort of the right way to approach least squares, because oftentimes people think of least squares kind of as a geometric operation. This really kind of codifies it as an optimization problem. And then after we finish that, we'll go on to our review of linear algebra, hopefully giving you whatever background you need, refreshing yourself to be able to make it obvious what we did in that derivation there. So, okay, see you next time.